Hello and welcome. It's me, Mitchell.
And me, Ethan.
We're coming at you live from self-isolation. And today we're sponsored by Corona, the refreshing beverage to get you through apocalyptic times.
And we're here today to talk about water, but not just water analysis, and specifically cation group 5.
So the main reason we test for water is to ensure that it's still wet. Never mind me. That's just a little water-based punditry there. On a serious note, why do we test for water? Well, water can embed and have harmful things inside it, such as different types of ions, mercury for instance, or diseases such as cholera and typhoid. So what we do at water treatment plants is mainly to test and cleanse our water so it is ready to be able to be drunk, washed in, and many other things you do with lovely water.
More specifically on the ions that we'll be looking at, which is ammonium ions and cation group 5 ions. With ammonium ions, we don't want too much in our water, but there's always a small amount present due to disinfection and purification of our water, and this small amount is normally in the very small quantities of parts per million. And then with group 5 cations, which include sodium, potassium, and lithium. Sodium, we always like a bit of sodium. It's helpful for our own bodies in general, and the same with potassium. But lithium, we don't really need it or use it, but it can be present in very small quantities, but we really don't want it at all in our water, as large quantities can become toxic. Some cations don't have insoluble solids that we can test for. These include the alkali metals, which the best way to test for them is by a flame test. And there we go. Flame seems to be working properly. We'll move on now.
Whoa, hold your horses. Let's first talk about how the flame test works. When the sample is placed underneath the flame, electrons in the ground state are excited as they're given energy. This then forms an excited state that's of higher energy than the ground state. When these electrons then come down from the ground state, they emit energy in the form of a wavelength.
Light, basically. And different cations of these groups will have different wavelengths that they emit, and obviously different lights associated with them and colours.
Let us elaborate more on the flame test. On the table on the right, there is a list of group 5 cations and the colour they produce when in the flame test. How do we perform the flame test, you ask?
Well, it's easy enough. You take your centrifugate from after doing group 1, 2 and 3 cation analysis, and you get a piece of wire, you dip it into your solution, your centrifugate solution, put it in a flame, in this case blowtorch, and it will produce the colour, and you can associate that colour to your cation.
Another group 5 cation test is the ammonium ion test, and what this is to test for NH4 positive ions within our water solution. How we do this is we add a base to the original water solution. This will produce NH3 gas, which rises up and reacts with the moist red litmus paper, turning it blue. The reason this is done at the start and not after all the other individual tests is because during those tests, NH3 is added as well to find other cations. This would lead to a false positive if there wasn't any NH4 positive ions in there. So we do it at the start to ensure that we have either yes or no for NH4 positive ions.
So as a pair, we've decided to analyse the unknown solution B. All of the information and tests were provided to us by Simon Bott due to current circumstances that we can't perform those tests ourselves. So let's go ahead and have a look at those cation tests.
The analysis of the unknown sample B yielded positive results for the group 3 cations, which are cobalt, zinc, chromium, iron 3+, aluminium, and nickel.
There were two main positive results from these tests. For the test for iron, yielded results. As shown, there was a precipitate of this water-iron complex that formed a solid shown in figure 5. This was after adding the sodium hypochlorite. And then after a test with adding the thiocyanate yielded a red precipitate, this iron thiosulfate complex shown in figure 6. And what this meant is that in sample B we had some F3 plus ions, and then there was positive results for zinc ions after adding some iron cyanide into the solution. It yielded a precipitate. In this case, it wasn't red, but was meant to be red. So we're just going to change that to red, like so, shown in figure 7. What this means is that we have some zinc ions as well. So from these tests, we can see that we've got iron 3 plus and zinc 2 plus ions in our solution. Further analysis of the unknown sample B proved positive results for group 5 cations. These include lithium, sodium, potassium, rubidium, cesium, and ammonium ions.
On the left here, figures 10 and 11 show a positive result for potassium. This is because a lilac-y glow is formed when the sample is placed under a flame. There is a problem with this type of analysis, like the flame test, the qualitative analysis, and it's based on judgment, which kind of leads, if you have poor judgment, to wrong decisions. For example, if you're colourblind, you wouldn't be able to distinguish between a red glow and a green glow. This is why we've moved more to quantitative analysis, such as spectroscopic things like ICP, which we'll introduce later on in the presentation. And then on the right, on figure 12, this shows a positive result for the ammonium ion, as the red litmus paper has turned blue when a base was added to the original sample of the water.
As well as our qualitative analysis, we did some quantitative analysis, which was using spectroscopic data of our unknown sample B. This was performed by taking the UV vis of several stock solutions of iron to generate a calibration curve. And from this calibration curve, you can identify the concentration of iron that is in our original sample. As you can see here, our calibration curve is a very nice straight line, and using the gradient of the line as well as the equation of that line, it correlates to the Beer-Lambert law. And by simple rearrangement and plugging in of values of our average absorbance of our unknown B, we get a concentration of iron to be around 7.4 times 10 to the minus 5 molar, which is reasonably low.
Another way to test for ions in your unknown water solution is via ICP, also known as inductively coupled plasma. And what it is, and what it does, is it determines trace concentrations of an element based on its atomic emission spectra. It uses electric fields to ionize argon within the machine, which can then collide with the cations and anions in solution to cause further ionization. This will then cause a temperature change, which could be detected by the machine, and each different element and cation has a different temperature change. This could be correlated into the amount of, or the concentration of said ion or cation in solution. And with our one, it's found to have iron 3 plus and zinc 2 plus. The iron has around 0.187, which isn't a lot, and the zinc is quite a lot at 6.113. ICP isn't the best technique and it's not very good. It's usually coupled with something like mass spec to help increase its validity of results and how much you get from it, because there is other ions in our solution, but it did only detect iron and zinc, which means it's not very good.
So, to conclude, in our water sample B, we found that we have iron ions, zinc ions, potassium ions, and good old ammonium ions. So that's it. Stay safe, and remember, stay inside because it's coming to get you. Good night, God bless, long live the great nation of Zimbabwe.